Now, in this class we will continue to discuss our first chapter. So, in that chapter now we are going to discuss ideal fluid. Ideal fluid is said to be a fluid having no viscosity, or this is also known as inviscid fluid. Inviscid fluid means having no viscosity. So, sometime it is very easy to develop the formulation by assuming fluid as a ideal fluid. It leads to very simplified equations, and if we have a simplified equation, then its solution is also very easy. So, sometime it is better to assume flow as a ideal fluid, though we know that in nature we do not have any fluid which is having zero viscosity. Even in case of air, the viscosity is not zero, it is very less, but it is not zero. But in many practical situations we consider it as zero, and we develop some governing relationship. With the help of those we solve the equations, and sometime we give very accurate result even with this kind of assumption, which is not very correct. Because in fluid mechanics the problem is that we have large number of variables. So, when we have large number of variables, then the equation becomes very complicated. So, that is the problem. So, to simplify it, sometime we assume that fluid is the ideal fluid. So, if viscosity is considered 0, then it leads to very simplified equation. Now, we have this figure. In this figure we are going to study the deformation. It is on x axis. Deformation is on x axis, and du tau shear stress on y axis. Shear stress tau on y axis and du over dy velocity gradient on x axis. So, when we have a ideal fluid, then ideal fluid will follow this x line, because mu is equal to 0. So, shear stress tau is equal to mu du over dy will be 0. And if we have a solid, then solid will follow the y axis, because in case of solid we do not have du over dy, because in case of solid du over dy is 0, because shear stress does not depend on velocity gradient. It is function of strain only, not strain rate. But in case of Newtonian fluid we have a straight line. Now, this straight line is inclined, and this inclination is dependent on coefficient of viscosity. So, if we have a straight line, then tau is said to be proportional to velocity gradient rate, or du over dy. Now, if we do not have proportionality constant as linear one, then there may be we may have non-Newtonian fluids. So, in like blood or sugar in water, these type of fluid come in the category of non-Newtonian fluid, where shear stress is not proportional to velocity gradient rate. Now, we may have some kind of plastics which follow this path. Up to this point, these type of plastic follow and behaves as solid, and after that they starts behaving like a fluid. So, this is ideal Bingham plastic, and then we have a plastic where we have this kind of variation for tau and du over dy, right. So, in this figure what we have learned the variation of tau versus du over dy for different type of fluids like Newtonian fluid, non-Newtonian fluid, plastic and ideal Bingham